While exploring or modeling data, we often need to look at how variables may be related to one another, what data instances may share similarities, and what major clusters or themes may exist in the data. The common task here is to measure the similarity, proximity, or distance between two entities, such as two variables or two data instances. Many related similarity and distance measures are based on the concepts of sets or factors. So let's review them before we look at similarities and distances. We have discussed categorical variables with values from a set of labels. A set is a collection of member objects or elements. The elements can be any unique entities, symbols, names, or numbers. The number of elements in a set is referred to as the cardinality. A tweet, for example, can be treated as a set of words appearing in it. In this case, the elements are the words and the cardinality is the number of unique words in a tweet. Consider the scale sets of two data science teams A and B. It is easy to count the number of skills in each team and identify their cardinalities. Their intersection, or what they have in common, is the set containing math and SQL, as illustrated by the shaded area in the figure. The intersection operation is commutative, and the order does not matter. Now, if we are to put the two teams together on one project, the overall skill set of the merged project team will be the union of the two. Because a set contains only unique elements, those in the intersection will be double counted when the two teams are merged, and should be removed from the union by subtracting the intersection. The union operation is also commutative, and it does not matter whether you add B to A or A to B. In addition, both the union and intersection operations have the associative property. As illustrated in the figure 1, we can obtain the same union set, the shaded circles, regardless of which two are combined first. The same is true with intersection, as shown in figure 2. The union operation is similar to addition, whereas the intersection operation can be likened to multiplication. To demonstrate this similarity, let's look at a couple of special cases. Let 0 denote an empty set with no element at all. 1 be the universal set containing all elements. For a regular set A, we can show the similarity between union and addition. The union of a set A and an empty set 0 is A itself, so A plus 0 is still A. The same is true about adding an empty set to the universal set 1. The union of A and 1, the universal set, is not exactly 1 plus A, but 1, but they too are roughly the same as long as the universal set is much greater than set A. Likewise, intersection and multiplication are similar. The intersection between a set A and an empty set 0 is always an empty set. This is like A times 0 equals 0, and 1 times 0 also equals 0. The intersection between a set A and a universal set 1 is A, and you can think of it as A times 1 is still A. In fact, for any set A that is a subset of B, their intersection is A, and their union is always B. Now we have looked at the similarity of intersection versus multiplication and union versus addition. The notion of set is applicable to events in probability. In fact, the concept of intersection is related to the joint probability of multiple events, which can be computed by multiplication. Union, on the other hand, is related to the OR probability, for which probabilities are added together. Besides union and intersection that can be likened to addition and multiplication, there is also the subtraction operator on sets. For two sets A and B, A minus B computes the difference between A and B, or the elements of A that do not appear in B. This is essentially the removal of their intersection from set A, as shown in the figure here. If A and B have no intersection, A minus B is the same as A. If A is a subset of B, then the result is an empty set. Subtraction here is not commutative because A minus B is not equal to B minus A. Let's talk about vectors. In geometrical terms, a vector is an entity having both a magnitude, length, and a direction in the vector space with multiple dimensions. The figure here shows data v1 and v2 in a space with x and y dimensions. In the vector space, each data point is a vector from the origin, as shown as directed lines in the figure, and can be represented by its dimensional values. So in this representation, a vector is simply a list of its coordinate values, each of which represents a feature dimension or a variable. The greater the number of dimensions, the longer the list of values. A set can be represented as a vector as well. For example, suppose AI, InfoVis, Math, Python, R, SQL, and Stats is a comprehensive set of skills for data science teams. Given A and B teams and their skills we discussed earlier, we can have the binary representation as shown in the table here, where 0 represents the absence of a skill and 1 denotes the presence of that skill. By populating the 0 and 1 values in the fixed order of the skills, we obtain the vector representations for teams A and B identical to the table. The vector space has 7 dimensions here, which correspond to the 7 skills in a comprehensive set, to represent instances of data science teams. These vectors are raw vectors, as they represent data instances. Note that here we use the superscripted AT and BT, where T stands for transpose, because of the convention of using column vectors by default. So without the T, it's a column vector. By transposing the column vectors A and B, we turn it 90 degrees counterclockwise and obtain the row vectors AT and BT. Here, each column vector is a column of 7 rows of real numbers. By transposing the column vectors, we obtain row vectors, each of which has 7 columns of numbers. With the ideas of sets and vectors, it is now easier to discuss several classic similarity or distance measures. Let's first look at similarities based on sets, the dice and Jaccard coefficients. Dice coefficient of sets A and B is 2 times the cardinality of AB intersection divided by the sum of their cardinalities. Jacquard's coefficient is similar. It's computed by the cardinality of AB's intersection divided by the cardinality of their union. So to show you an example of how to compute the dice coefficient, these are 2 teams and 2 sets of skills that we discussed earlier. First, we compute the cardinality of their intersection, which is 2. And then we compute the cardinalities of A and B individually. Now we can compute the dice coefficient by dividing 2 times the intersection by the sum of their cardinalities. A second example to compute Jacquard, again with the same 2 sets A and B. Again, we compute the cardinality of intersection. In the second step, instead of computing the individual cardinalities of the teams, we compute the cardinality of the union. And Jacquard is simply the intersection divided by the union. Now let's look at vector similarity and distance. Minkowski distance is actually a family of distant functions. In the formula here, we use u and v instead of a and b. V for a vector, so it's easier to remember. So in the formula, there is a parameter called p, which is the order of the distance function. And we refer to the distance as the distance of LP norm depending on the value of p. When p is 1, L1 is the Manhattan distance, which is the sum of absolute distances along the dimensions. Think about you walk on the streets of Manhattan, and the way you measure the distance from one place to another is to add the number of blocks east-west plus the number of blocks south-north. When p equal to 2, L2 is the Euclidean distance, or the line distance of 2 points. Let's look at an example to see how we can compute the Manhattan distance and the Euclidean distance using the 2 vectors u and v, which actually represent the teams A and B that we discussed earlier. Here we are having 2 vector representations instead of 2 sets. For Manhattan distance, or L1 norm, we first calculate the difference of each dimension or each column in the vector representation and get the sum of their absolute values. For L2 norm, which is Euclidean distance, the difference here is that we need to compute the square of the subtraction, add them up, and then take the square root of the sum. Here the Euclidean distance happens to be the square root of the Manhattan distance because of the binary representation. This is only a special case, and you will see that they behave very differently with real numbers. The vector magnitude is actually an application of the Euclidean distance from the origin. So the vector magnitude of v can be computed by taking the square of each value, sum them up, and take the square root. The dot product of 2 vectors is to multiply values of the 2 on each dimension and take the sum. This is the covariance of values in the 2 vectors, and the final score is impacted by 3 factors: the vector magnitudes of u and v, and the alignment of the two vectors, or to what degree they point to the same direction. In particular, you can think of the dot product as the product of the degree pointing to the same direction times the magnitude of u times the magnitude of v. Now that we know the dot product is a product of the three vectors, if we normalize or divide it by the product of the two vector magnitudes, the result will be reduced to their direction similarity, or to be precise, the cosine similarity. Let's revisit the example vectors and see how we can compute their cosine similarity. First, we compute the dot product of the two vectors u and v. Then we compute the magnitude of u and the magnitude of v, and the cosine similarity becomes the dot product divided by the two magnitude values. The cosine similarity measures the cosine of the angle between two vectors. It is all about the direction, and the magnitude of each vector does not matter here. It has been normalized by those magnitude values. Cosine varies from -1 to 1. Cosine reaches its maximum 1 when two vectors point to the exact same direction. Its minimum -1 is reached when the two vectors point to the opposite direction. Cosine is 0 when the vectors are orthogonal or perpendicular to one another. Cosine similarity is particularly useful in applications where the distribution of values is more important rather than the absolute values. For example, in text mining, it is more important to find out frequencies of terms relative to one another. Cosine similarity has performed very well in these related applications.